Okay, I have a new paper up. Want to do a quick discussion on it, get some ideas out there. It's, stellar metamorphosis, stellar axial angular momentum during evolution. Now, axial angular momentum is picture like a bowling ball or a basketball. When it spins around on its own axis, that's its axial angular momentum. Or like if you take a top and you spin a top and it spins and it stays upright, that's its axial angular momentum. The majority of angular momentum stuff you see when it comes to solar system objects is they have the object spinning around the sun, and that's their angular momentum. But there are different angular momentums. The one where it has the object spinning around the sun in orbit, that's its orbital angular momentum, and that's what you're going to see a lot of when you go online. For this, it isn't. I'm not referring to that. I'm referring to the object itself spinning on its own axis, how much energy it's spinning with. And as a rule of thumb, the reason why I wrote this paper is that as the star evolves, its angular momentum decreases because its mass decreases and its radius shrinks. So, of course, this is after blue giant stages. I still have to work out the white dwarf stuff because that's going to be really crazy. I think those things are really massive and they're spinning really fast, so which means they're really young. So I guess really. the okay, I just want to explain how this works. Uh, I'll go more in depth with it later, but for now, you have three main components to figuring out the angular momentum of a spinning object. You have your L, which stands for angular momentum. You have your I, which stands for the moment of inertia. And then you have your omega, which looks like a W. That stands for its angular rotation rate. The omega, which is the angular rotation rate, is 2 pi radians. 2 pi radians. So you take, it's just like the circumference. So circumference is 2 pi r, 2 times pi, which is 3.14, times the radius to find the circumference. But with radians, it's 2 pi radians. And that's all it means. It's just, radians is just another word of saying radius. So 2 pi times this is the entire circumference. And then you take the entire circumference and you set that to 1 by putting seconds underneath. So I did some math here. Let me show you what one of those looks like. You know what? Just pull up the paper. It's written too small. You'll see it. And of course I'll go over this more in depth as I continue working on it because there's a lot of stuff here. But basically, you take the moment of inertia and you multiply it by its angular velocity, how fast it's spinning. And of course, the moment of inertia has 3 main components. The I has 3 main components. You'll see in the paper. The I has its angular, moment of inertia factor, which is 2/5 for an undifferentiated body. Of course, I set it to 2/5 because that's just an assumption. I can change the moment of inertia factor because yes, they all are not 2/5. Some of them are different. Its mass, how massive these things are, and its radius. So you have 3 components for the moment of inertia, and then you have 2 components for its angular velocity, which is you set the whole circumference to 1 and then you multiply it by seconds, which is going to be really low, obviously, because the Earth doesn't spin once every second. It spins once every, 86,400 seconds. So you'll see that in here. But basically, I wanted to really drive this home. The rate of spin of a planet diminishes as it evolves because it loses mass, it shrinks, and it experiences tidal forcing from the gravitational fields from other bodies as well. There's very little bit of solar radiation pressure that can slow it down as well. The object switches around inside as it changes orbits sometimes as well. There's differential rotation internally. I have that in another paper. But think of like a water bottle. Say you have like a water bottle that's a little half empty like this, and you try to roll it on a table, it kind of jitters and it slows down. Same thing with a star. If the star has fluids inside of it and those fluids swish around, it's not going to maintain its same rate of spin over time. Which means it's gonna slow down significantly until the internal fluids completely solidify, and by that time it's just like Venus. It's rotating very, very slowly. And what's interesting about this, and I have these calculations in here, is that even though, here, where do I have that written down? This is in the paper, you can find it. Even though Mars is 13 times less massive than Venus, it has about 4.9 times the angular momentum as Venus. What that tells me is that Venus is extremely old. Not only that, but the Earth itself has about 166 times the angular momentum as Venus, even though Venus and the Earth are about the same mass. And I think that's really interesting because I also measure the DH ratios of Venus compared to Earth, and I have Venus between 100 and 150 times older than the Earth. So to think if I can also pinpoint the amount of angular momentum in there as well for its age, that would be phenomenal. That would just be crazy. As well, it's also interesting to see that Mars has 4.9 times less angular momentum as Venus, meaning Mars is obviously a lot younger than Venus as well. Now, this is a shot in the dark, but Mars is easily 4.9 times younger than Venus. I know that's a jump in thinking, but with Venus's 450 billion years old, oh my gosh, it's just all over the map. I have more work to do on this, but I just wanted to show you these calculations and to give you a feel of when you look at these objects, when you study them in the future, when astronomers start publishing the exoplanet rotation rates, how fast they're rotating, you should be able to look to see if they're really, really old or not by just how fast they spin. Here's Earth, Mars, and Venus. These are their angular momentums. Earth is 7.06 times 10 to the 33 kilograms meter squared times seconds over seconds. So I have the -1 exponent. That means seconds is on the bottom. That's per second. Mars is 2.082 times 10 to the 32. Venus is 4.267 times 10 to the 31. So in essence, it's like stepped. You have one being 10 times more, have more angular momentum than another, which is 10 times, and another roundabout. Of course, I'm generalizing for that, but just to give you a refresher on, 10 to the 33 is 10 times more than 10 to the 32, which is 10 times more than 10 to the 31. It's exponential stuff. But yeah, I just wanted to talk to you guys about that, and I'm gonna upload these calculations as well. I did Saturn, I did Neptune, I did Uranus, I did a hypothetical white dwarf, I did Jupiter, and they all match that line of evolution, to where the younger it is, the more angular momentum it will have. And I'll just go ahead and tell you these while I'm at it. Jupiter is 4.49 times 10 to the 38. You see that? And then you have Saturn is 6.91 times 10 to the 37. So you drop an exponent and it's a little bit less. Like almost 10 times less. More like 8 times less. And then Neptune and Uranus, and here's the really interesting part. I have them based on the DH ratios being about 100 million years in age difference. Neptune being about 100 million years younger than Uranus. And wouldn't you believe it, Neptune's angular momentum is 1.54 times 10 to the 36, right there. And Uranus is 1.3 times 10 to the 36. So around 0.2 times 10 to the 36 difference in its measured angular momentum. To think if I can use that and backtrack and weigh it against the DH ratios. Anyways, I think I made this video long enough. I'll go ahead and post these new diagrams to the paper. And the paper's already up. I'll just make a newer one, and I'll link it to the bottom. All right, guys, take it easy.